OK，那我们开始了。OK，it's a great pleasure today to have Chen from BIMSA to tell us about fusion rules of excitations in topological order. Let's welcome.
Thank you for the introduction. It's a great pleasure to give a talk here and tell you about topological order and the boundary excitation of topological order. Okay, this work was completed when I was doing my PhD at Fudan University. It was collaborated with my supervisor, Professor Ling Yan Tong, and my colleague, Liu Jiaqi. We had 2 papers for this topic. This TRL is for bosonic anion condensation, and later we generalize it to fermionic anion condensation. Before diving into the details, let me first give the outline of the talk. So first, I will introduce the topological order and its boundary, the boundary excitation and boundary defects. Then I will introduce a topological number for half linking number, and then use the half linking number to deduce a formula for the edge excitation. Then I'll give 2 examples, both Abelian and non-Abelian example. And at last, I will briefly mention how to generalize it to fermionic condensation. So the concept of topological order has a history of a few decades. So first is Xiaogang Wen, Frank Wilson, and Anthony Lee. They first proposed the notion of a chiral spin space. They used the chiral spin space to attempt to explain the physical mechanism of high temperature superconductivity. It was later found that this chiral spin space contains a new kind of order, which is beyond the conventional Landau symmetry breaking paradigm. And this new kind of order is called topological order. The name topological order, it has the name, is because that it's no energy effective theory, it's topological quantum field theory. So at very low energy scale, the topological order is just a DKFT. There are many systems that have topological order. For example, the fractional quantum Hall system, and the Topological, and also the Levin-Wen model. They all show topological order in the system. Yeah. Topological order describes spaces of matter that are not characterized by local order parameters or spontaneous symmetry breaking. It has several key features. For example, the fractionalized excitation. The quasi-particles in topological order may carry a fraction of charge of fundamental particle. For example, the anion in the fractional quantum Hall system, they carry a fractional electric charge. Another feature is the ground state degeneracy. The ground state degeneracy is the number of the ground states. Is the number of ground states, and this degeneracy, this number depends only on the topology of the manifold, and it is invariant under any local perturbation of the system. Another one is the long-range entanglement. This means that the topological order cannot be brought to a product state by a series of local unitary transformations. And this is the property that Xiaogang Wen used to define a topological order. In his definition, the topological order is a system which has long-range entanglement. This is exactly distinguished from other phases such as STT phases and symmetry breaking phases. Well, to make things precise, when we say topological order, we can either mean an order parameter, which is a topological invariant, or we can use topological order to refer to the physical system that has these properties. So in our talk, I will use topological order to refer to such a physical system. Okay, the mathematical structure of a topological order on a 2-dimensional compact manifold is described by a unitary modular tensor category. So here we only require this 2-dimensional manifold is compact. We do not require it to be closed, so it may have boundaries, and it is the case where this manifold has boundary is our main interest. In topological order, there are quasi-particle excitations called anions. Anions are some local excitation. Anions are modeled by the symbol object in a UMPC. Anions can fuse. The fusion rate is given by the ring structure in the UMPC, and anions can break around each other because So we're considering a two-dimensional system, so anyons can break each other. And this breaking is given by S matrix in the UMTC. And anyons have spin. The spin is given by the T matrix in UMTC. This S and T matrix, they give the representation of SLQZ. The S matrix element are algebraic integers, and the T matrix element is given by e to the 2 pi HA. Here HA is a rational number. This is proved by Baha. This HA is called the spin of this anion. If this spin happens to be an integer, then this anion is a boson. It behaves like a boson. If you move it around another boson, then so if you exchange two such anions, then the global phase acquired is just one. If this spin is a half integer, then this anion behaves like a fermion. And in general, this spin can be any fractional number, so it can have fractional statistics. This boson and fermion are emergent boson and fermion. They are not some fundamental particle. So let's do some recap of the data of modular tensor category. This might be familiar to many of you, but let me just summarize. Anyons can fuse, and they have the fusion rule given by the fusion coefficient Nijk, which is a non-negative integer. We can characterize the fusion space by the fusion trees. Here, each fusion tree has two input legs and one output leg. And the fusion can have some different fusion channels characterized by this mu. So mu can take value from 1 to Nijk. And the dimension of this fusion space is just the fusion coefficient Nijk. Anyon fusion is commutative. So if you fuse I with J, it has the same effect of fusing J with I. So Nijk is symmetric about its Ij indices. Anyon fusion is also associative. So for such a fusion space, BIJKL with 3 inputs and 1 output, you can either fuse I and J first, and then fuse it with K, or you can fuse J with K first, and then fuse with I. So these two different fusion trees, they provide two different bases for the same fusion space BIJKL, and we can do a basis transformation. This basis transformation is given by F symbol. The authorship of the entity has a strong constraint on this F symbol. If you consider a slightly larger fusion space, which has 4 input legs and 1 output leg, then one can show that associativity requires F to satisfy an equation called the Pentagon equation. And in this same fusion space, we can obtain that the fusion coefficient satisfy this relation. And if we group this fusion coefficient into a fusion matrix for Ni, whose Kj element is called Nijk, then this means that this relation means that the fusion matrices Ni, they commute with each other. So we know that if the matrices commute with each other, then they can be diagonalized simultaneously. And it turns out that the fusion matrices are simultaneously diagonalized by the F matrix. And the eigenvalues are SIR over S0R. Here the 0 is the vacuum object in the MTC. Verlinde has shown that there is a relation between the S matrix elements and the fusion coefficient. On the right-hand side, the sum over R is over all the anyons in the MTC. So in a modular tensor category, this Verlinde formula can be easily shown by considering this picture. So consider anyone long n and few anyone loops around I and J. We can either consider each output loop I around anyone long n. Then this gives a number S2mi over dm. Here dm is the quantum dimension of anyone n. And we choose such operation and we get this coefficient. Or we can first fuse this to anyone loops. We can fuse anyone loop I and J, and we get sum over Nij K around 10. And we apply this relation here to get such a factor Nij K S tilde over dm. And we let these two coefficients to be equal. And from this relation, we can get the Verlinde formula. This is the simple proof of a Verlinde formula in the modular tensor category. Okay, this is the Verlinde formula for the anion fusion in our bulk theory. Next, we will generalize this to the fusion of boundary excitation. Okay, so much for the theory in the bulk. Is there any question of this part? If no, let's continue. Next, we will consider a gap boundary of a topological order. So if we consider a two-dimensional manifold which has a boundary, and if we put a topological order on this manifold, then for this system, at the boundary, there might be some gapless chiral edge state. For example, the chiral Lavender liquid in fractional quantum form. This KLL is the chiral Lavender liquid in fractional quantum form system. Some topological order is chiral, and some topological order is non-chiral. And for those non-chiral topological order, on the edge, there are left moving and right moving modes, and the number of left moving modes is equal to the number of right moving modes. So we have the equal number of left moving and right moving, and then we can introduce an interaction term. This interaction term can potentially open up the energy gap. So we have a gap boundary. This picture is a time slice of this gap boundary. So we have a 2+1, so two spatial dimensions of this order, and this boundary is one dimensional, one spatial dimension. So this is the time slice. The other side of the boundary is the vacuum. This bulk is given by MTC, and this boundary is given by fusion categories. So the boundary excitations are a symbol object of this fusion category. Physically, this fusion category has no breaking structure. This is shown physically because the boundary only has one spatial dimension, so you have no extra room to break to boundary excitation. Kong Liang has proved that the bulk modular tensor category is the junction center of the boundary fusion category. So we have the relation bulk equals center of boundary. And our aim of the research is to obtain the fusion rule, is to get how these boundary installations use with each other from the bulk UMTC data. Okay. Physically, we have a boundary relation given by the anion condensation. So anion condensation is a process where certain anions gather together at the boundary and merge in a way that they form a new kind of stable state. The basic idea of anion condensation is that when moving close to the boundary, some anion can vanish, they can disappear and enter the vacuum phase, while others cannot. So mathematically, the anions that can condense at the boundary form a Lagrangian algebra in this modular tensor category. The Lagrangian algebra is a special case of a commutative symmetric Frobenius algebra. The Lagrangian algebra is used to describe a gap boundary between a topological space and the vacuum, while the Frobenius algebra is used to describe the gap interface between two different topological order, for example, the B and B prime. Then we have a Frobenius algebra to describe the excitation. Okay. The Lagrangian algebra defines a bulk to boundary condensation sampler FA from B to C, which take each anion on B to A tensor A. In this anion condensation process, it's useful to mention that we require fusion and condensation to commute. This means that we can, for example, if we consider two bulk anions and bring them to boundary, we can first fuse them in the bulk and then condense the anion to the boundary. Or we can condense the two anions to the boundary and then do a boundary fusion. We require that the two methods give the same result. Informally, what we call condensed anions are the anions in A or the kernel of this sampler FA. If under this condensation sampler, above anion gives a trivial a vacuum boundary object, then we say that this anion is a condensed.
So here the B is a UMTC.
Yeah.
And the C is just the fusing chemical.
Yeah.
What's the X?
X represents a boundary excitation. For a boundary excitation is a simple object in the fusion factor.
It is used to be topological over B. I mean, if C is just a fusion category, how does it interact with B?
What do you mean by interaction?
So B the frequency. What I mean is that according to graphical, and this C should be a multi-category over B. So that they are
Yeah, the A is a Lagrangian algebra. So C
See
is
the
a,
module category.
it's a module category of B, and moreover, B is the center of C because A is a Lagrangian. Yeah.
So in this anion condensation process, some particular types of anions can condense at the boundary, can cross boundary freely to the vacuum phase. Here, by free, I mean it has no energy cost. It can cross this boundary. While other anions are stuck at the boundary, they cannot move to the vacuum phase. And those anions are called confined. So we have condensed anion and confined anion. Now let's give two examples to help you understand the condensed and combined anion. So the simplest example is the Topological model. So in the Topological model, in the bulk, we have 4 different kinds of anions, 1, E, and F. In the system, 1, E, and M are bosons, and F is a fermion. And the fusion rules is given by CP cross CP. The 4 fermions force square to the vacuum, and the fusion of E and M gives them. In this Topological model, we have 2 different boundaries, the electric boundary and magnetic boundary. So in the electric boundary, the Lagrangian algebra is given by 1 plus C. And the corresponding condensation factor, we have listed the effects of this condensation factor and map each block anion to some boundary excitation. So you can see that anion 1 and anion E, they are mapped to the same 1 plus C as the boundary, and anion M and F are mapped to M plus F as the boundary. In this case, the condensed anions are 1 and E. So at this electric boundary, anion 1 and anion E can cross this boundary freely and enter the vacuum. While the M is stuck to the boundary, so M is confined, and 1 and E are condensed. The boundary excitations are given by the result of this condensation function. So if we look at the right-hand side of this condensation function result, we see that there are 2 different particles, boundary particles. First one is 1 plus C, and the second one is M plus F. And we have 2 boundary excitations. And the fusion rule is just CP. Another boundary is a magnetic boundary, which is symmetric to this one by replacing E with M. Basically, the structure is the same. The only difference is that here in this case, the condensed anions are 1 and M, while the anion E the concept not cross. So we also have 2 boundary excitations, 1 plus M and E plus M. Only fusion is this one fuses itself with the future object in the fusion category. So boundary fusion category has the C2 structure. The Topological model is an abelian example, and we give also a non-abelian example. This is the Fibonacci bar model. The bulk anions are 1 bar, 1 tau bar, tau 1 bar, and tau bar. And the fusion rules are given by tau tensor tau is 1 plus tau. And in this model, 1 bar and tau bar are bosons. And 1 tau bar and tau 1 bar are some arbitrary anions. Their charge is fractional. In this case, we have a diagonal compensation given by the Lagrangian algebra 1 bar plus tau bar. one can prove that this is actually a Lagrangian algebra in this MPC. And we can give a compensation bunker for this Lagrangian algebra. So we also do the calculation and bring each bulk anion to the boundary. And we see that on the right hand side, it beautifully organizes itself to two different particles, namely 1 bar plus tau bar and 1 bar plus tau bar plus tau bar. So we can persuade ourselves that that on the boundary there are two different boundary excitations labeled by 1 bar plus tau bar and 1 bar plus tau bar plus tau bar. And boundary excitation, the boundary fusion category is the same as a single Fibonacci fusion category. This is a non-Abelian example. And so in this case, we can see that for the bar anion, its behavior is under this condensation bunker is split in two parts. This one is condensed and this one is confined. So this is a feature of a general non-Abelian anion condensation. So the concept of confined anion is well defined in abelian topological orders, where the point dimension of each anion is equal to 1, and the fusion algebra reduces to a fusion group. The Lagrangian algebra also reduces to Lagrangian subgroup, fusion group. And confined anions are cosets of A, and boundary fusion is given by a quotient group B over A. However, as we have seen just now, for a non-abelian topological order, it may happen that a bulk anion breaks into two parts, where the first part is condensed and the second part is confined. So in this case, we need a more fine mathematical structure to describe confined anion. So the confined anion, which gives the boundary excitation, is given by a module of A. So the boundary fusion category is a module category. A module can absorb the left action of A. Is given by a pair. It's given by M, and also an action rho AM. There is some associativity relation for this module category. Okay, we have another more physical way to describe this bulk to boundary relation. This is given by W matrix. The W matrix essentially has the same information as the condensation bunker. So we have a decomposition A equals sum over X, WX. In this W matrix, the first index A labels the bulk anion, and the second index X labels boundary excitation. The W matrix elements are non-negative integers. It measures how much contribution a bulk anion has to a boundary excitation X. So this W matrix is also called a branching matrix by physicists.
So this is FAA equals W to the right?
I mean, if you list the result of this condensation bunker, then you can write down the W matrix.
No. Left hand side, A is the object of B. The right hand side is the object of C.
Okay. Yeah.
So you should write FA of A on the left hand side. Then you have something in C.
Okay. Yes, that's a more mathematically rigorous. So this question means that we bring the bulk anion A to the boundary and we decompose it into several boundary excitations. If WAX is greater than 1, this is the non-trivial multiplicity, the non-trivial condensation multiplicity of bulk anion A decomposing into boundary excitation X. So in this case, in the case where WAX is greater than 1, we have different condensation channels. We need extra index to label this condensation process.
Oh, no, okay. This is correct. This is fine. You can write this.
So at the boundary, the trivial object at the boundary corresponds to a trivial module A, and the condensed anions are the bulk anions, which have a WC0 greater than 1. So the condensed anions are anions that actually condense to the boundary, to the trivial object at the boundary. And we define a condensate. We define the set of all condensed anions to be a condensate. We use the symbol CP. It's proved by Wang Zhenghan. There is a reciprocal condition in this boundary relation. So if we consider bringing a bulk anion A to the boundary, then it composes to several boundary excitations. This is given by W measure. We can also consider a converse process. We can have some boundary excitation X, and we bring this boundary excitation X to the bulk. Then this boundary excitation disappears and excites several and produces several bulk excitations in the bulk. So this same process is also given by the same W measure. This second equation is saying that the boundary X is several bulk excitations. They are all described by the same W measure. It is useful to distinguish a boundary excitation and a boundary defect. So up to now, we have only considered one type of a uniform boundary. So we have a bulk B and a boundary C, and the boundary excitation are the particles, are called the particles that live on this one boundary. It is objects of the boundary fusion category. We can also have a boundary defect. A boundary defect, as shown in this picture, it's some excitation localized at the junction between two different boundaries. So we have a bulk B and its two different boundaries, mu and nu. Then this boundary defect is the excitation localized at this junction. It cannot move along the boundary. The boundary defects they are simple objects of the multi-fusion category. The multi-fusion category is not a fusion category. Naively, it can be the sum of all the fusion categories and not all the objects at the junction. Boundary excitations and boundary defects is also closely related to the topological defect line in CFDs. It was first proposed by the confined and super, and then developed by mathematicians. Okay. So in these two pictures, a boundary excitation is given by a module, and a boundary defect is given by a mu bimodule. Because the two boundaries they have the same bulk. So according to the bulk equals center of boundary relation, we don't have that the junction center of CU and the junction center of CU they are the same. They give the same bulk of MTC, so they are Morita equivalent. Okay, this is the mathematical structure of boundary excitation and boundary defects. We have put them in a general framework of the multi-fusion category, and our work is to write down a fusion rule in this multi-fusion category. Okay, from the nature of the condensed anion and confined anion, let's record that condensed anion can freely pass the boundary, and confined anion are stuck at the boundary. They cannot move across. From their nature, we can define a natural topological number for tap linking. So this is the picture for the tap linking number. This is a non-Abelian generalization of the tap linking number in the gap boundary of Abelian transcendent theory, first given by Shen and Salina. So our tap linking number is a non-Abelian generalization of their work. So we look at this picture. This line is the boundary line. So we can create a boundary excitation at the boundary. Then we create X and the particle. Then we create a condensed anion C from the boundary, and we move it around X. And finally annihilate it at the boundary. So we have a half loop. Then we also annihilate the pair of X, opening up the X line. So this picture is a topological number, and this is our tap linking number denoted by gamma XC. Here IJ denotes the non-trivial compensation channel. The corresponding W metric element is greater than 0. Sorry, is greater than 1. If there is no extra condensation channel, then you can simplify some X. Here X is the boundary excitation and C is the condensed anion of this boundary. Okay, this is the half-linking number for one boundary. We can generalize it to the junction to different boundaries. So this is the half-linking number for boundary defect. So we have boundaries mu and mu, and boundary defect x mu localized at the junction. We do the same thing to give a half-linking number from x. The sequence mu is to denote that this number is between boundary mu and mu. Here in this case, the anion, it can pass the mu and mu boundaries, so it must lie in the intersection of the two components. Only the condensed anion shared by the boundaries can you can have such a half loop. And I mu and J mu are condensation channels. Okay, we are going to use this half-linking number to derive fusion rules, the boundary excitation and boundary defect. So let's consider our system. Our system is a topological order B here, and we have three different, perfectly different and consecutive boundaries, mu, mu, and rho. Here X is the boundary defect between mu and mu boundary, and Y is the defect between mu and rho boundary. We have such a visual system. The other side of the boundary is the Kaplan phase one. If we are going to shrink the middle boundary to nothing and bring these two boundary defects x and y together. So the result is that they fuse to boundary defect z in boundary mu and rho. This is the physical process, and we can write down the fusion rules that x fused with y is x y is sum over z. Here we use little n to denote that this fusion coefficient gives the boundary defect fusion. Record that in the box, we use capital N to denote the anion fusion coefficient. So in this process, we can obtain a formula for the fusion coefficient of the boundary defect, given in this way, given by the half-linking number gamma matrix. This formula has a very similar form to the Verlinde formula in the bottom. So we give the name of defect Verlinde formula. This is used to calculate all the fusion coefficients of boundary defects. In this equation, the sum is over sum of C is over the intersection of three boundaries, and this second sum is the sum over all possible compensation channels. This m is just a normalization constant. So we obtain this formula by the following way. We consider a similar, we consider this picture. We have the x mu loop and y mu rho loop and the anion lines the threading two loop. Then we can do two things. We can either deform this line to bring it close to the new boundary and break it at the boundary. Then we have this picture here. Or we can first shrink this new boundary and bring the two boundary defects together to fuse the two boundary defects. We can get this here. So we require that the result of this A and B process should be the same. So roughly we can see that this is the gamma matrix, and this is gamma x, and this is also gamma y c, and this is gamma z c. So we can write down an equation which looks like gamma equals sum over b and x one. This one is distribution. And there is a normalization factor appears in this process. When we break the C line at the new boundary, there is a loop around the trivial object, this new boundary, and this effect is given by the normalization factor and C. So if we replace this MCU by the gamma 0 C mu here, in this Verlinde formula, we can see that it has the same form as the Verlinde formula in the box. This is why we call it the defect Verlinde formula. Okay. Is there any question on this? If not, let's continue. Okay, good. We have explicit formula to for the boundary defect solution rules. So the next thing is how to compute this gamma xc matrix. We are led by the following facts. For a gap boundary, for one topological order and two different gap boundaries, the number of defects that is localized at the junction, the number of the defects is equal to the number of condensed elements here by two boundaries. And this first equality is simply saying that the gamma matrix gamma xc is the square matrix. So x labels the defects and c labels the condensed elements. So this is telling us that gamma xc is a square matrix, and this number is then equal to the ground state degeneracy on a cylinder. So let's consider a topological order put on a cylinder with top boundary mu and bottom boundary mu. So this is saying that if we consider a picture like this, which we have drawn before, the bulk contains category B and boundary fusion categories C mu and C mu. This is boundary defects. Then the number of defects is equal to the number of shared condensed anions C, and this is equal to the ground state degeneracy of a cylinder. So we put the same topological order on cylinder here, and we use the same boundary condition mu and nu. So this is C mu boundary and this is C mu boundary, and on the bulk we put a B. Then this is saying that the number of defects here is equal to the number of shared condensed anion here, and it is equal to the ground state degeneracy for such a physical system for the topological order on a cylinder. And if we consider this system, the topological order on a cylinder, we can find that it has two sets of bases. Its ground state substrate can be spanned by the Wilson loop basis or by the Wilson line basis. The Wilson loop basis is labeled by one anion, and the Wilson line basis is labeled by the shared condensed anion C. It makes sense because if you consider the physical process of anion condensation, then we see that the condensed anion, the anion that freely move across the boundary to the vacuum, then they just disappear from the box, and what are left over on this loop is just the confined anion. Only the confined anions are left over around this circle. So the confined anion or the defects are used to label the Wilson loop basis. Similarly, in the Wilson line basis, this line can touch the top and bottom boundary, so it must lie in the intersection of the two condensates. It is the condensed anion that are shared by the two boundaries. So we have now we have two description of the ground state subspace of a topological order on cylinder. For these two bases, we can also write down a basis transformation, and it turns out that the basis transformation between the Wilson loop basis and Wilson line basis is exactly given by the gamma matrix. So we can write the X loop basis is equal to sum over C gamma. Here, this sum is over commutating channels. If you ignore this second sum, it's just X equals sum over C sum X. So it's a basis transformation. And we can use this property. We can use the fact that gamma matrix is a basis transformation to calculate the matrices. Before I give you examples, I will show the striking similarity between the bulk S matrix and the boundary gamma matrix. So here is the table. and we list the similarity between the two topological numbers. So first, the definition of an S matrix is just a Hopf link of two bulk anions after normalization. And the boundary gamma matrix is defined as a half link. So there is similarity between their definition. And for the fusion, the S matrix gives the bulk fusion coefficient, and the gamma matrix gives the boundary fusion rules for boundary defects. Then, if we consider a 2+1D topological order on a torus, the torus is the spatial dimension of the topological order. So if we consider this topological order on a torus, then this topological order also has two set spaces. One is given by anion groups around the large circle, and the other one is given by anion groups around the small circle. And the basis transformation is given by the definition. And this one is just shown before. It's the 2+1D topological order on a cylinder. So on a cylinder, this gamma matrix gives the basis transformation between the Wilson loop base and Wilson line. Also, for 1+1D CFT, this S matrix is the matrix representation of the S transformation, which brings tau to the 1/. And we have also proved a similar formula for gamma matrix. So in another paper, we have proved that for 1+1D CFT whose voltage is such a cylinder, then we can prove that the open string character is related to the closed string character in a similar way, given by gamma matrix. So these are the similarities between S matrix and gamma matrix. It's useful to mention that the Lagrangian algebra corresponds to a modular invariant CFT, and the boundary defects correspond to the defect line in CFT. So we have established the correspondence between S matrix and gamma matrix. Also correspondence between the bulk and the boundary. Okay, now let's get two examples, an Abelian and a non-Abelian one. The first is the quantum double, Abelian quantum double, DG, where G is the Abelian group. For a quantum double, its boundaries are given simply by the subgroups of G. Here, we consider DG on cylinder and the two boundaries Knu and Knu. Knu and Knu are subgroups of G. In this case, we don't need to write down the Lagrangian algebra because it reduces to just subgroups. We can use the subgroup structure to write down all the boundaries of the DG. And it turns out that the gamma matrix is calculated as this form. It's proportional to SXT in the bulk. And we can use this gamma matrix to we can use our defect Verlinde formula, and we use this gamma matrix, and we can calculate that the fusion coefficient is exactly x1b equal to delta x plus yb, which is very intuitive. You just in the Abelian case, you just use x and y together. There's nothing else. It's just a simple delta function. Okay, the next example is the non-Abelian quantum double example, DS3. In this case, we put a DS3 on the cylinder. So for this bulk DS3, it has 8 different kinds of anions labeled by A, B, C, D, E, F. In this DS3, there are 5 bosons, A, B, C, D, and F. There are 5 bosons. And for S3 group, we have 4 different subgroups, namely the P1, P2, P3, and P4. And correspond to these 2 subgroups, we have 4 Lagrangian algebra labeled by A1, A2, A3, and A4. So for this DS3 bulk, we have 4 different boundary groups. And we give a table which shows the boundary excitation and boundary defect. So in this table, we have 4 boundaries, A1 to A4 and A1 to A4. So in the diagonal cells, we give the boundary fusion category. For example, in this one, this means that the fusion category at this A2 boundary is given by factor 2. And the boundary fusion category at A3 boundary is given by reference 2. For the non-diagonal cells, this gives the number of boundary defects and the common dimension of these defects. For example, here, this means that at the junction between A1 and A3 boundary, there are 3 boundary defects. They all have common dimension vertical cube. So this table gives all the information of the boundary defects of the boundary of quantum double DS3. And we can use the basic transformation trick to calculate all the gamma matrices. This is the result. And then we can use this gamma matrix to write down all the fusion coefficients of all the boundaries of the DS3. We just show a simple one between the A1 and A3. So we consider the defect fusion between boundary A3, A1, and A3. So we shrink the middle A1 boundary, and the result is the fusion. And the result is the boundary excitation at A3 boundary. So we use our defect Verlinde formula, and we can calculate all these fusion rules with respect to this boundary configuration. So the first result was obtained by Fudan, and the following results are obtained by they do not have the following result. The following results are calculated using our defect Verlinde formula. So at last, let me briefly mention how we can generalize this same process to fermionic anion condensation. So for fermionic anion condensation, we have some emerging soft fermions, and we pair these soft fermions with free fermions at the boundary, and they form a Cooper pair. A Cooper pair behaves like boson, so we can condense these Cooper pairs. This table is the difference between bosonic and fermionic anion condensation. So in a fermionic anion condensation, both bosons or fermions can condense, and we should replace the Lagrangian algebra to a super Lagrangian algebra. Also, the boundary fusion category to a boundary super fusion category. We have W matrix and omega matrix, and we can generalize the defect Verlinde formula to a fermionic version. The special thing about fermionic anion condensation is that it has a J2 gradient given by A1 plus A2, and this omega matrix is similar as W matrix that replaces the A by A2, A1 minus A0 minus A1 here. And in the boundary superfusion category, one can also write down the super pentagon equation, which in a middle set for one inserts a fermion dot here.
Where is the pre-fermion coming from? Because I saw this is the gap boundary. As the pre-fermion, it seems like the available. This is like a gap more in boundary.
We can use a thin structure at the in this case, and we can create Majorana fermions at boundary and use this free fermion at boundary to pair with block fermion.
Oh. Okay.
And this is our result. It's basically the same as the bosonic case. Here, I just some label, and this is some dimension of complex. It basically has the same structure as the bosonic case. Okay, so today I've introduced the topological order and its static boundaries, the boundary excitation and the boundary defects. Also, we introduced a half-linking number to compute the boundary fusion of the topological order, and we give a defect Verlinde formula, which is similar to the Verlinde formula in the bulk. And we also give Abelian and non-Abelian examples. And we mentioned how to generalize this to fermionic boundary. That's all. Thank you.
Great. Thanks for the great talk. Are there any questions?